I am very proud of giving this talk, and it is great pleasure for me, first of all, because I, I can acknowledge memory of late Professor Yudovich with this talk, who was my teacher, who was outstanding mathematician and real gentleman, first of all, as one British professor said me about him. So I'm I realize that the audience is not very much familiar with mathematical fluid dynamics. So I'm planning to outline briefly the basic notions, then setting the problems by Yudovich, and then break through and groundbreaking results in the field. So how to operate this thing? So you can read, I would like to cite Vladimir Arnold, who mentioned the notable exception of Yudovich. He was, of course, notable exception in many respects, but Arnold meant that Yudovich never believed in the lacking of global regularity. And he explained his disbelief by enormous resistance of the problem to any attempt to prove blow up. But by blow up, I mean spontaneous breakdown of solution in a finite time. So let's discuss setting of the boundary value problem. You see, it's we have to use this. This is Euler equation. This is initial conditions. X capital is the flow map. This is indicates the motion of fluids, of fluid as a physical substance. So we can, by this substitution, we can rewrite this equation. But this is, I'm sorry. It's a very special case of Euler equation, the incompressible dust flow. And this is a way to integrate it by characteristics. And you see from this implicit equation that the collapse seems inevitable. But we can avoid it if we consider if d null is nilpotentus. Then this series is just a polynomial. And it turns out that the incompressible fields, initial fields, gives rise right to these nilpotent matrices. If we take, we can just easily construct the example. For example, you can see here.
Is this only sufficient condition?
What? Yes, it's sufficient conditions, but I think it's necessary too, but yes.
In what function space do you look for solution?
Here, it's almost in smooth, all the data are smooth. This time we deal with dust media, no pressure. So we can integrate it by hands, implicitly, just to reduce to functional equation. And this is the case when these functional equations are globally solvable. But you can see that if we evaluate the vorticity of this flow, it's incompressible, but the vorticity grows linearly. And this is this is a good example of resistance. So the dust media is well known to be singular. The blow up is almost inevitable, but if we add incompressibility, we reduce the opportunity of blow up. We avoid it fully. So this is the references to so-called philosophical papers of Victor Osich, where he discussed his seeing of main problems in mathematical fluid dynamics. And now we are about setting of the boundary value problem. Here you see its pressure. So its velocity, both v and p are unknowns. V is vector field, p is scalar field. This is in Cartesian coordinates. This is covariant derivative, of course. And the question is, does this boundary value problem has a global smooth solution? This problem remains unsolved up to the date, despite of great efforts of many outstanding persons. So local existence is well known due to classical papers by Günther and Lichtenstein. And after many authors proved it in various functional spaces, but I would like to discuss one special geometrical setting. So if we introduce the flow map, then we can write this equation in so-called Lagrangian form, and then we can treat this Lagrangian form as Euler-Lagrange equation arising from the least action principle of Hamilton, and this is the Hamiltonian function, the Hamiltonian of the system. So Arnold considered this Lagrangian as Riemann metric on the group of volume-preserving diffeomorphisms, and in his well-known work, he put it into the abstract context of special reduction of geodesic spray equation to the first order equation in the Lie algebra. Due to the right invariance of this Hamiltonian with respect to right action of the group S diff on itself. And then Marsden and Deben showed what is the Arnold operates formally and the main difficulty is that this group is not a Lie group because it is infinite dimensional group, and the main problem is that left shift is bad, it's not differentiable. Right shift is good. So They showed that local geodesic spray of this metric exists on the Banach manifold modeled on HS when S greater than n popolam plus 1. In 3D case, this 2 1/2. So this gives us classical solution because this is embedded in CC1 alpha for velocity. Yes, they consider 10-dimensional case, but we will discuss n equal to 2 or 3. Now here you can see the conservation law. They are due to the right invariance. In fact, I mean the conservation law for circulations. You can treat it as a equality between cosets of homological one forms. And this one, so-called vorticity conservation, arises from this one by applying external differential. And so on. In 2D flow, these invariant sets in the phase space of Lagrangian system can be shifted to the Lie algebra of this formal Lie group, which is the space of solenoidal divergency-free vector or divergency-free vector fields, and in this space they form this shift form some foliation consistent of isovertical leaves. Next, in the 2D case, we have crucial simplification because we can the vorticity has only one component which can be treated as a scalar function. It persists. It preserves the vorticity conservation is just a rearrangement of the vorticity values, and the leaves of the vertical fields can be identified with equimeasurable functions. Now we get to the question of generalized solution. You see the divergent form of Euler equation, and this divergent form results in weak formulation. But there are no global 3D results, even if we take initial field in C0 infinitely smooth. And there are no local 3D results if we take V0 in L2. But L2 is the natural energy space. So Udovich estimated the problem of global weak solution as a hard, very hard, but not terribly hard. Not so hard as the global regular smooth solution. Well, something positive about weak solution. First of all, there exists finite weak solution. This means strong non-uniqueness of the weak solutions. There are many weak solutions. Next, there is a global weak 2D solution for the vertex sheets. Vertex sheets is the measure valued verticity concentrated on, say, for some smooth line. It's popular model, physical. Also, these guys with very complicated names proved that there are infinitely many weak solutions in 2D for initial vertex sheets with non-constant signs. The Lord proved this for sheet of constant with verticity of constant size. This is well known in fluid dynamics that vertices of different signs behave much more in much more complicated way than the vertices of equal signs. So they proved that there are infinitely many solutions, which in some sense not conservative, but they do not allow energy to grow. They are dissipative in some sense. So there are no any dissipative terms in the initial original problem. And also there are some progress in Anzeiger conjecture, so it is fully proved. There are examples that for lower Hölder exponent there are no energy conservation, and it must be for supercritical exponent if we prove existence of suitable solution. But if we find such a solution, it will be conservative. So how much time I have now? 6 minutes. So I would like to skip many things and to go to must. I hope you have already understood enough to eat the main course. I would like to discuss very recent results on the collapse of classical solution. It's very sophisticated thing. They are due to the company where I think I don't know them, but I think this guy Elgendy is the leader, and around him there are such persons like Drivas, and one more guy with Chinese Jeong. They do some excellent work, excellent job. So first, if we would like to prove the collapse, we operate. Let's go back to the vorticity equation. You see, where is it? Well, I think I missed it when I was prepared. So the vorticity equation reads as where omega stands for the rotor or curl, And this term, and the V stands for the fields of velocity. So this is the transport, pure transport. And this is quadratic nonlinearity, which, one can say, oh, this is the problem with quadratic nonlinearity. Open any textbook in differential equation and you will see an example of blow up. But this is very special nonlinearity because it takes the form FSF, where S is singular integral operator. Then we express V, oh, I'm sorry, omega nabla V. So if we express nabla V by vorticity, we have zero order PDO here. And this is very sophisticated thing. So Fokash and Maida construct a model problem, one-dimensional, where S is singular Hilbert operator on the line. And they found collapses. These guys tried to construct such a solution. They considered axially symmetric flow with no swirl around the axis. So for this flow, the vorticity is also can be expressed as a scalar, which is directed, the field is directed azimuthally everywhere, and that's why we can take the absolute value of this vector as a scalar, and this scalar, they want this scalar to take this form. And this form presumes blow up, as you can see. And then they proved that such the function f exists. First, they proved that there exists such a solution for model problem like this. Not the same, but similar. Then they extended this, they add some transport term, and they get this result for the vorticity equation. But this is bad thing in the sense that the velocity has unbounded energy. And then they proved that this singularity persists if we take only the path and construct, if we cut out the vicinity of singularity and placed it into more regular on the infinity field. And they proved this that all these things get the singularity, but they are honest gentlemen, and they do not state that they solve the problem. Problem of global regularity is not closed, is not finished, because look here, please. They prove their construction do not work for if we add, even if we choose C alpha with alpha greater than 1/3. So this works only for classical solution, but do not work for smooth solutions. If we consider they don't know any infinitely smooth initial field to which lead to blow up. So, as Viktor Osich said, the problem keep resisting. Thank you very much once again.